My dear friends, welcome to Rajshekhar classes on applied data science with Python. This is lecture number 556. In this lecture, we will try to understand dropout layers and regularization. So let's understand very important idea called dropout in deep multi-layer perceptron, in deep neural network in general. In deep learning, dropout is brilliant idea and we will see how it creates regularization. The most important thing is when you have deep neural network, when you have deep neural networks, deep multi-layer perceptron, the biggest problem we are facing is overfitting. We will never underfit. What is deep neural network means? It means you have many layers, you have many hidden layers. What do you have? You have many weights, and you have many weights that you have to train. Given this potential of training many weights, the biggest problem we encountered is the biggest problem we encountered is overfitting. You have to always look for avoid overfitting cost. We saw that to avoid overfitting we can use L1 regularization or L2 regularization. Dropout is another super powerful technique. It's actually extremely simple and elegant. It is simple and super elegant. It is brilliantly elegant. This whole dropout technique is discovered in 2012 by master students Nitish Srivastava along with Geoffrey Hinton. We know that Hinton is godfather of backpropagation. Nitish is used to work as master student under Hinton. It is Nitish master's thesis. Let's recall random forest. We already discussed about random forest in our previous lectures. What do we do in random forest? We basically sample. We basically sample a subset of columns, because in random forest what we build, you build many trees, isn't it? We build many trees, simple decision trees. We build many trees in the sense, simple decision trees. We build trees. Instead of taking all the features or columns, you only take subset of features. Suppose we have trees tree 1, tree 2, tree 3, tree 3, so on. I can say tree k, tk. Each tree only looks at subset of features. That's important. Each tree only looks at subset of features. Remember, the decision trees that we are training in the case of random forest are fully grown decision trees. In random forest, what do? We have fully grown decision trees. We have decision trees of full depth, which are actually overfit models, isn't it? Which are actually overfit models. We are taking random subset of features. When you train each of these trees, we take random subset of features, and what do we do at the end of it? We train multiple trees like this, and we simply take majority vote. This is like quick recap of random forest. So in random forest, intuitively what we are doing two important things. First one, we are taking random subset of features and train each of base learners. Here what we are doing, we are using randomization, isn't it? We are using randomization. In the case of random forest, we are using a form of randomization for regularization, isn't it? The core idea is using randomization to create regularization, because we are taking random subset of features, isn't it? We are taking random subset of features. This is important. We are taking random subset of features. Each of the trees that we are building here are using random subset of features, even though they might overfit individually, because you are doing majority vote at the end. Because of each of trees are overfit, because each of the trees are overfit using random forest. We are regularizing, isn't it? Because of each of trees are overfitting using random forest, using random forest, I can say we are regularizing. You have overfit models, that means high variance models. You have high variance and low bias models as high variance and low bias models. High variance and low bias models as base learners. Here base learners are T1, this T1, T2, so on, TK. These are base learners. Just see, these are high variance. This basically, what is this trees? They are basically high variance and low bias models. That point is very important. I will repeat. You have high variance and low bias models as base learners. Here base learners are T1, T2, T3, so on, TK. Through this randomization and majority vote, we are reducing the variance, isn't it? What is this? Through this randomization and majority vote, we are reducing the variance, which is nothing but regularization. So the core idea is random forest. We are using randomization of features to create regularization. That's what we learned in random forest. If you forgotten some of these details, please go back and revise it, the chapter in random forest, isn't it? The idea in dropout is, can we take the same concept randomization for regularization? Can we take the same concept but apply to neural networks, is like multi-layer perceptron? That's the core idea. Let me explain how they do it. So this idea actually, because when I first read it, I did not understand it thoroughly. I read the paper couple of times. And connected the dots with the random forest. I also listened to brilliant talk that Hinton explained why dropouts working things like that. So in the description section of this video, I will give you the link to actual research paper which explain the dropout networks in lot of detail. Here, this is your I can say this is your input layer, this is your layer 1, you have layer 1, you have layer 2, and even I have output layer. Let's assume this is my neural network. This is xi1, xi2, xi3, so on, xi4, and the what is this yi cap? Here your output is yi cap. These are your activation functions. What are the activation functions? These plus symbols are activation functions, and these two are layer 1, layer 2 are two hidden layers. So what dropout suggests you to do is this: at any point, whenever you are doing forward propagation, or backward propagation, see, at the end of the day, we use back propagation, but what it says is, in any given iteration, so for example, in this iteration we have 5 inputs here. Just see how many inputs we have: xi1, xi2, xi3, xi4. At any iteration, in any given layer, randomly makes a subset of input, subset of your functions. Remember, this function generates, for example, this particular function in layer 1 generates out. Just see, this function generates output. Which function? Let me say I have function, this function generates output. This will become input for the next layer neuron, isn't it? Which is input to the other function. What it says is, take this point is important. Take a bunch of neurons in your input layer or hidden layer and randomly remove all the connections that are incoming or outgoing from that neuron. So you randomly pick. This is your fully connected. This is your fully connected multi-layer perceptron. Let's assume I have a patch input that I am sending it through. So when I do forward propagation, when I do forward propagation followed by backward propagation, I randomly remove connections. Suppose I remove this a neuron this neuron randomly. When I randomly remove it, all outgoing connections are disconnected, all the incoming connections are disconnected. So literally looks like this, isn't it? If I randomly remove bunch of inputs and bunch of activation functions, basically I am removing them only for that iteration, isn't it? When I remove them only for that iteration, what happens? The network no more looks like fully connected networks. All these are disconnected units. That into mark things are disconnected. All these are disconnected units. And what I will do here, there is a term called dropout rate. There is something called dropout rate. In dropout rate is basically the dropout rate is basically a probability. It is often written as p, 0 less than or equal to p less than or equal to 1. So if I say p equal to 0.2, my dropout rate is 0.2. What it means, in any layer 20% of neurons will be inactive or they are dropped out. 20% of neurons are inactive or dropped out in any given iteration. So here I think they set p equal to 50%. So what happens out of the 5 inputs here? What are those 5 inputs here? Here 2 of them are off, are dropped out, are inactive. Here again you have 5 neurons. Just see, here again you have 5 neurons here. Randomly if you take 50%, 3 of them become inactive or dropped out. Again you have 5 neurons. Here again 2 of them become inactive. So in total, how many neurons you have? Total you have 15 neurons, input neurons and hidden neurons. 7 are inactive, isn't it? 7 by 15, isn't it? These are inactive just for this iteration, or they have been dropped out, and in the next iteration different set of neurons will be dropped out. It is not the same set and it is a different set. For this iteration, let's assume 7 are dropped out. In the next iteration, probably other set will be dropped out. I request all of you to go through this lecture, and I will continue my discussion on dropout layers and regularization in my next lecture also, that is in lecture number 557. Thank you very much.